4-3 notes, I wanted to come back to this idea really quick because I actually misspoke the other day. I was mistaken on what they're expecting of you when they ask this type of question. So when they want the coefficient, I said that they just wanted the number from the essentially the choose piece. I was mistaken. They actually want the entire coefficient. So say we were trying to find the coefficient of this one, so let me just start this from scratch. So remember, we have that binomial theorem that tells us how to expand these out in really gross and terrible ways. And essentially, if we have that, this is a wow. that first piece is essentially the A value, if you will, and the 2 is the B value. Then essentially, we always have that their powers are going to add up to 10. So if I have x to the 7th term, that would give me that I must have had a power of 3 on the 2. And then the coefficient in the very front comes from essentially the power that you want to expand it out to, and then choose the power on the B term. Oh, I don't know if that made any sense. Sorry, I'm writing the wrong thing now. So we want to expand it out to the 10th, and essentially that B term turned out to be 2 to the 3rd, so we're going to do 10 choose 3. 10 choose 3, I already had it written down. I should have left it there because I don't remember what that is. I think it was 120. Yeah. But when you're actually answering this question, the 2 cubed turns into 8. So then this term in general would actually reduce down to 960 x to the 7th. And the 960 is actually what they want. So sorry about that. Let me do one other quick one really quick, and I'll hold on a second before I do that one. So the thing that I mistakenly said was I said that you only cared about the choose thing in the front, but you actually care about the whole entire piece. So essentially, what if we did another one really quick? Say I wanted the coefficient for the, let's say, x to the 4th term in the expansion of, let's do 2x plus 3 to the 6th. So essentially, if we're taking the x to the 4th term, I want to take that first, 2x and take it to the 4th. So we want to take that to the 4th power. So if both of these powers need to add up to a total of 6, that would mean we would be squaring the 3. And we'd have 6 choose 2 in the front. The top thing in the choose is the power that you're expanding it out to, and the bottom number is whatever power your B term is. So then 6 choose 2 is something. 6 choose 2. Let me just write it out like this really quick. So 6 choose 2, that would be 6 factorial over 6 minus 2 factorial times 2 factorial, to remind us the factorial notation. I'm just using my calculator to cheat and do this really quick. And then 2 to the 4th is 16, so we would get 16x to the 4th, and then times 9. So if we multiply all of those constants together, you would get 2160x to the 4th. So the coefficient that they want would be the 2160. So it goes a little bit more than I had originally told you. Sorry about that. All right, questions about that before we finish up 4-3? All right. I did hit record, right? Yes. Okay. Oh, sorry. Yeah, Dakota, that's exactly what I was doing. Is if you have a newer calculator, you type the 6 in first, and then you hit the math, and you scroll over to the probability one, and you hit that NCR, and then you type in the 2. So essentially, I feel like I did that wrong. Hold on one second. 6 choose 2, yeah. Yeah, so you type in the 6, and then you hit the math button and get to the NCR thing. And then essentially it should end up looking like this on your screen. All right, so let's jump over to 4.3 then. Oh, sorry. Yeah. So, once again. So there's a couple different ways you could do it. If you were doing it in your calculator, you could just punch it into your calculator. Or remember that when we're doing 6 choose 2, it's 6 factorial over 6 minus 2 factorial times 2 factorial. So if you don't remember how to put it into your calculator using the choose button, you can remember the factorial way. So we essentially have 6 factorial over 4 factorial times 2 factorial, which essentially, so 6 times 5 times 3 times 2 times 1 over 4 times 3 times 2 times 1 times 2 times 1. So essentially the 4, 3, 2, 1 can cancel out. And we have 6 times 5 over 2 times 1, so 30 over 2, so 15. Let me, one moment. Let me pull up my little calculator doodad and remind y'all how you can do that in your calculator really super duper quick, in case me just saying words isn't helping. Oops. So in the calculator, of course, again, you can always do it the factorial way and just reduce the factorials into your calculator. But if you want to do, say, 6 choose 2, you have to type the 6 in first. And let me pull up my key history there. And then you hit the math button, which is right below the alpha. And you have to scroll over to the probability one. And then if you want the permutations, you hit number 2. If you want the combinations or the choose, you hit number 3. So if I want 6 choose 2, I can do that as well. Hold on, I'm having a problem resharing my screen. Come on. You can do it. Still being a little dumb, so we're gonna have that little thing in the corner, but at least it got shared now. So otherwise we have to finish up for 3 notes. I'm not entirely sure it'll take the entire time, and if we have time at the end, I can take questions about your exam coming up. But anyway, let's try to finish this kind of quickly. There we go. So we got to talk about something called, well, they're oddly called many-to-one functions, and that's because there's a bunch of different ones that many can be a number. It can be whatever number you want. Well, maybe I shouldn't say any number you want, any positive number. So a function from some x to y is going to be called n-to-1 if every y, the image of the function, so essentially every output, has exactly n different elements of x that map to it. So remember, we can have multiple inputs mapping to the same output, so that's perfectly okay. So this is essentially saying that we have n inputs mapping to the same output. And that's exactly what this notation, this set notation at the bottom here is saying. It's saying that essentially the cardinality, which is what those kind of absolute value bars are at the outside, the cardinality of the set of x values, so the set of inputs, such that that input gives you y, would be n. There would be n things that map to that y value. So remember, we talked about one-to-one a lot. It kind of came back up in the beginning of 4.3, but we initially talked about it way back in chapter 2, and that was essentially saying that there was only one input that went to every output. Now we're saying that we can have multiple inputs going to the same output, and it has to be the case that all of the outputs have the same amount of inputs going to them. So let's say we look at sets 1, 2, 3, 4, 5, and 6, and then our output set, or our possible outputs, are 0, 1, and 2. And we want to define a function by essentially modding by mod 3, taking these numbers and doing mod 3 to them. So let's kind of write out what the values of this function would be. So if I want to take, and we're calling this function m, so instead of using normal f notation, we'll just use m instead. So say we have m of 1. That would be, what is 1 mod 3? Well, since 1 isn't greater than 3, we don't really need to worry about changing it at all. So 1 mod 3 is just 1. And then what about 2 mod 3? Well, 2 mod 3, again, 2 isn't greater than 3 or equal to 3, so we don't have to worry about changing it really. So 2 mod 3 is 2. And then once we get to 3 and so on, that's when we're going to get a tiny bit more complicated. So remember, modding, technically you're finding those numbers. It's technically the remainder after you divide that number by 3. So if we take 3 and divide it by 3, since 3 is divisible by 3, the remainder is 0. So 3 mod 3 is 0. 4 mod 3, 4 divided by 3 goes in once, but then has a remainder of 1. So 4 mod 3 is 1. Let me know if you need a little bit more work written out about those. 5 mod 3, 3 goes into 5 once with a remainder of 2, so 5 mod 3 is 2. And then 6 is actually divisible by 3, so 6 divided by 3 is 2 with a remainder of 0. So since the remainder is 0, 6 mod 3, is 0. Now the point of that was, look, we've got, wow, that, okay, that works, I guess. We have those two go to 1. These two go to 2. And then, and how do I want to make this box slightly different? Make the side squiggly. And then these two go to 0. So essentially, if we take just those numbers and just that mapping to be our function, essentially every input went to one output, but every output got hit twice. So our outputs were 0, 1, and 2, and each one of those had 2 inputs that went to it. So essentially, this function is 2 to 1. Because every output has 2 inputs that went to it, because, so that's exactly kind of what this does next, because 2 numbers in X map to 0, 2 numbers in X map to 1, and 2 numbers in X map to 2. So again, it has to be the case that all of the outputs have that many inputs going to it. So say we were only going, say X was only 1, 2, 3, 4, 5, and we didn't have that last term in the back here, then that wouldn't be 2 to 1 because 0 only got mapped to once. So it has to be the case that all of the outputs get mapped to the same amount of times. But since all of the outputs here had 2 inputs going to them, it would be considered 2 to 1. If we wanted to depict this a little differently, say with our little maps that we've looked at every once in a while. So remember the map in math is, you know, these two bubbles that go to each other. So we have our inputs on this side, 1, 2, 3, 4, 5, 6, and our possible outputs on this side. And then remember, we draw the arrows between them if they match up. So 1 map to 1, 2 map to 2, 3 map to 0, 4 map to 1, 5 map to 2, and 6 mapped to 0. When you draw it out like this, it's kind of easy to see that all of the inputs only go to one thing, so that's good because that's what we need to be a function. But each output has 2 arrows coming into it. So it'd be 3 to 1. We would need each one of those outputs to have 3 arrows. If it was 4 to 1, they'd need 4 arrows, and so on and so forth. Bad network quality. Okay, pause for a second until that goes away. Usually comes back in a hot second. There we go. So when it's written out like this in a map, it's kind of easy to see they have to have the same amount of arrows going to each output piece. So let me even write that down. So each element in Y has 2 elements mapping to it. So where'd you go? Nope, that's not what I wanted to do. So say we want to consider whether or not a function can be 1 to n. So notice that this is different. We were talking about n to 1, and now we want to talk about 1 to n. So what that would mean, what this means, so this means that one input has n outputs. So before, with the n to 1, that would mean that one input has n. Nope. Output has n inputs. Sorry, so one output has n inputs, but this would say that n outputs have one input. So essentially one input has n outputs. Sorry. I don't think that made any sense. I should not say that that way. But essentially that's what 1 to n would mean, that one input has n outputs. Well, that can't happen because if we're asking this to be a function, remember, for something to be a function, every input can only have one output. If inputs have more than one output, that can be a relation, but it can't be a function. So the function will not be well defined. Would not be well defined. So essentially, if anyone asks you, can a function be 1 to absolutely any number besides 1? The answer is no. So a function can be 1 to 1, but it can't be 1 to 2 or 1 to 5 or 1 to 7 or whatever. It can be 7 to 1 or 3 to 1 or something like that, but you can't start with 1 to some other number that's not 1. So going back to the idea of n to 1, if every, y value in the image, which remember the image is just the fancy name for the outputs, the set of outputs. So if every y in the image has exactly n different elements that map to it, then we actually have some relationship between the number of elements in x and the number of elements in y. What that's going to be is, say you have p elements in your input set and q elements in your output set, and there's some n to 1 function between the two. What's going to need to happen is of elements in your input set is going to have to be n times the number of elements in your output set, which makes sense because if every element of y is mapped to the same amount of times, which would be n times, this makes sense. Because again, if every input can only go to one thing, but every output has n things going to it, then the amount of inputs must be n times the amount of outputs, which is exactly what this is saying. The amount of inputs is n times the amount of n outputs. So that's what we call an n-to-1 function. Questions about that before we go to a slightly different idea? Okay. So what we have to talk about next is something called the pigeonhole principle. So say a pediatrician needs to give a little girl 3 vaccinations, and these shots are going to be given in a leg. So can the little girl receive 1 shot in each leg? And by that I mean only 1 shot in each leg. Well, no, unless she's an alien. Well, maybe not an alien. There's probably people out there who have 3 legs. But we're going to assume this is a, regular 2-legged girl. So no, she can't receive only 1 shot in each leg because she has 2 legs, which is not as many shots as she needs. There's 1 more shot than she has legs. So it must be the case that 1 leg will get 2 shots. Which is kind of the idea behind the pigeonhole principle. It's essentially like, say you have 5 pigeons, but only 4 nests. If every pigeon has to be in a nest, there must be 1 nest with 2 pigeons in it because there's more pigeons than nests. So the formal statement of the pigeonhole principle starts the following. We're going to extend it, in a little bit, but this is the, sorry, I have the hiccups. This is the initial statement of it. 1 moment, please. Okay, so let's say that the amount of elements in X is going to be n, and the number of elements in C is going to be R. And let's have some function from X to C. So if n is greater than the number of inputs is greater than the number of outputs, then there are distinct elements X and Y from the input set, such that f of X equals Y. So in other words, as I kind of was already trying to say, number of inputs is more than the number of outputs. Then 2 different inputs must have the same output. There's more inputs than outputs, then there must be at least 2 elements that go to the same output. Just like there's 3 shots to 2 legs, so there must be at least 2 shots in 1 leg. There's more inputs than outputs. Now, this isn't saying that you know exactly how many go to the same one. This is just saying that there has to be at least 2 of them that go to the same thing, because there's more inputs than outputs. We're not saying we know that there's only exactly 2 that go to the same. There could be more of them that go to the same output, but there has to be at least 2. So let's say that Stacy hates folding laundry, sounds like me, and tosses all of her socks into a drawer. She has 8 black socks and 12 white socks. She's in a hurry and reaches into the drawer without really looking. How many socks must she pull out to guarantee she has a matching pair? So the fact that we have to guarantee that there's a matching pair is the big buzzword here. So say we think about this in terms of like a function. If we took inputs to be the amount of socks she pulls, and then the amount of outputs, not the amount, the outputs are going to be essentially the color of the sock. So let me give these variable names. So let's call the socks pulled, it's going to be X. And then the color of the sock, well, we essentially have 2 options. It's either black or it's a white sock. So essentially the amount of colors, of course, then is 2. Now, if we think about it, if we want, the amount of socks pulled to have at least 2 of them either being black or 2 of them being white, we would essentially need to make sure she pulls more than 2 socks. So essentially by the pigeonhole principle, Stacy needs to pull more than 2 socks. Because if you think about it, if she pulls only 2 socks, it's not guaranteed that 2 of them that they're going to match. It's possible that they would, but if she pulls at least 3 of them out, then it's guaranteed that 2 of them are going to match because there's only 2 colors. So essentially we would need more inputs than outputs here to guarantee that 2 of them match. So since we know that the amount of outputs is 2, we know that we would need more than that for our inputs, so we need at least 3 socks that she has to pull out. Hopefully that made sense. Let me know if it did. Now, again, that's kind of the starting statement of the what is happening in my English? The starting statement for the pigeonhole principle, but we can extend it a little bit. We can generalize it. So the generalized pigeonhole principle, which looks a bit more notationally scary, essentially starts off the same way. That second theorem shouldn't be there. Anyway, so we're still going to let the amount of elements in the inputs to be n and the amount of outputs to be r. Now we're going to say if n is greater than r times l minus 1, then there is some subset of the inputs such that the amount of that subset is L. So we're essentially saying that there's a subset of L elements, and f of x equals f of y for any elements in those subsets. So essentially what we said last time is we said there's at least 2, and this is extending it more to say if you have this relationship here for some number L, then you actually have L elements that must go to the same output. So in other words, in more general English, if the number of inputs is a lot more than the number of outputs, then there are several different inputs that must have the same output. So again, the first one we looked at, L is essentially 2. We're saying that there's at least 2 of them that go to the same output. And here we're saying there's a set of L things that go to the same output. Now, there's kind of a corollary to this. Corollary, if you don't know, is just a thing that comes from a theorem. So a corollary to this is the thing that we're mainly going to use. And what that corollary says is it says let the amount of inputs be n and the amount of outputs be r, because then we're defining the function between the two. Then there is some subset of the inputs such that the cardinality of that set, so the amount of things in that set, is equal to the ceiling of n divided by r. Sorry, not n divided by n. And that f of x equals f of y for all of the elements in that set. So essentially this follows from the generalized pigeonhole principle if we just let L be the ceiling. So essentially what this is going to mean is that we're going to be able to figure out essentially the size of the set of how many things, at least how many things we're going to be able to figure out the size of the set for how many things oh my lord, my English. How many things must map to the same output? Now again, we're not saying that we know exactly how many, but we're saying based off of the pigeonhole principle, there must be at least this many that map to the same thing because of the situation that's going on. So say, for example, we have this example 4, a small college offers 250 classes, no 2 classes the same time in the same room, of course. And there are 12 different time slots for which each class can occur. What is the minimum number of classrooms needed to accommodate all the classes? So of course, we're saying there's 12 time spots and there's 250 classes. So essentially, how many classes must run at the same time? So how many classrooms do we need? So essentially, using this generalized pigeonhole principle and this little corollary, if we think about the inputs as the number of classes, well, I shouldn't say the inputs is the number of classes. I should say the inputs are the classes. And the number of, so let's name that X. And so then the amount of classes we have is 250. There's 250 classes at this college. Let's think of our outputs as essentially the set of time slots. Whoops. So let's name that C to kind of match up with the pigeonhole principle. So that means that the cardinality of our set C, our set of outputs, is 12. So we're essentially going to map a class into a time slot. Now, obviously, there's way more classes than time slots. So again, that's kind of what the pigeonhole principle is getting us to, is that there's going to be multiple inputs that go to the same time slot. So we can now figure out at least how many must map to the same one. And the way we can do that is we can look at, since we have a function from X to C that we can define by essentially by assigning a class X to a time slot C, then essentially that corollary that, can I bring it in here a little bit? That corollary up here, if we take the ceiling of 250 divided by 12, that's going to get us the number of classes that must go into a time slot, at least. So if we take the ceiling, 250 divided by 21. No, that's a bracket, not a ceiling. If you forget what the ceiling is, so if we find 250 divided by 21, we get 11.9. And so remember, the ceiling is essentially the least integer greater than that decimal. Now this decimal is a little bit longer than 11.9, but so the least integer greater than 11.9 is exactly Dakota 12. So essentially what this is saying is that we need at least 12 classrooms. Again, we don't know how they actually schedule it. They could have 15 classes running during one time slot, or 16 running during another, and whatever. But there has to be at least 12 classes running at one time for this setup to make sense. So there needs to be at least the 20. Whoa, no, I'm sorry. What am I doing with my life? Get out of here. I had a bit of dyscalculia when I wrote these notes, apparently. It's 21. I'm sorry. 21 was supposed to be the answer. So sorry, let me back up. So we need to take the number of inputs divided by the number of outputs. So 250 divided by 12, 250 divided by 12 gives you 20.8. So then the least integer greater than 20.8 is 21. So there must be at least 21 classes. I'm really sorry about that. Goodness gracious. So sorry, number of inputs divided by number of outputs. Take the ceiling of that number is what you want. So we have 250 inputs, 12 outputs. Take the ceiling of that. There must be, so essentially let me write the answer here. So there must be at least 21 classrooms. Sorry about that. questions concerned about that? Number of inputs divided by the number of outputs. Trying to pull up another one really quick because I just butchered that a little bit. So yeah, let's say, so the questions on that one, I'm going to pull another one kind of off the top of my head really quick. Just because I butchered that one a little bit. So say I wanted to say something like explain why in a room of 13 people, at least 2 must share the same birth month. Well, if you think about a function, so say our set of inputs is the set of people. So we have 13 people. And say our outputs is a birth month. Well, the amount of months in a year is 12. So essentially by the pigeonhole principle, because there's more inputs than outputs, because there's 13 people but only 12 birth months, at least 2 people must share the same birth month. And if we didn't know the number 2, we would have found it by taking the inputs divided by the amount of outputs and taking the ceiling of that number. So this is the ceiling of 1.08, which is 2. So there must be at least 2 people in that room that have the same birth month. Because of the pigeonhole principle. Again, of course, there could be, maybe all of them have the same birth month. Maybe 5 of them do. Maybe 3 of them do. But this is a case of essentially the minimum amount that must share something. So in this case, there has to be at least 2 people that share the same birth month. Does that make any sense? So that's the pigeonhole principle. I don't think you have homework on 4.3 because it would have been due today, and I don't think I did that to you. But it will come up on your exam. There's a few questions on it in on the review. So the review got up on Blackboard a couple days ago. The answers got up yesterday. I actually had to fix one of them right before class. I realized I added incorrectly. But that's the pigeonhole. Oh my lord, pigeonhole principle. Questions, concerns about that? Okay. That's the end of 4.3, and I don't even have 4.4 up to be able to start them. I wasn't going to do that anyway. We have about half an hour left of class, so I'll take questions if anyone has them. If we don't have questions, then I guess we'll just end a little early here. Well, a lot early, a little bit. But if you have questions or you have topics you want me to go over, or you want to glance over the review really quick and say, can you go over this type of idea? Can totally do that. Yeah, so your test is on Thursday. It covers, let me not lie to you. So as I've mentioned before, there's no induction proofs on the exam, but there is recursion. So there's the recursive data structures from 3.5. That was the, in order T for the binary search trees, the sum function, that kind of deal. So I'll ask you to use them, but not prove they work. So there's no induction proofs on the exam, but you only need to know how to do the recursive data structures. And then it covers 4.1 through 4.3. So 4.1 and 4.2 were those like addition and multiplication principles for the counting. And then the 4.2 was the arrangements and the selections, like our last quiz. So yeah, if anyone has any questions, I will answer them now. Homework, review, otherwise, floor is open. If you don't have questions, you're free to leave. I'm being slightly hesitant in case someone asks something. But if you don't have any questions, again, we're not moving on to 4.4. We'll do that after the exam. 4.4 is going to be most likely the last topic we cover. So we'll have, because we essentially, after our exam, we only have 2 classes left. We have a Tuesday before Thanksgiving and a Tuesday after Thanksgiving. So what I'm planning on doing is I'm planning on covering 4.4 on the 4.4 on the Tuesday before Thanksgiving, and then the Tuesday after Thanksgiving, I'm planning on just having kind of a big review session for your final. I'm going to use this time to do the review. The final is cumulative, yes. So that's part of the reason why I want to make that very last class kind of review, so we can kind of go over some of the topics from the very beginning and kind of refresh our brains on what things are. But yeah, so if you don't have any questions, I'll stick around. I'll just like stay in here if any of you want to like start trying the review on your own and then ask me questions when you have them. But otherwise. Should we just review the exam reviews for the final and for study material? So to have a final exam review as well, just like these exam reviews. But yes, I would say reviewing the past exams would be a very, very good idea. As I've said a couple times, this is my first time officially teaching this class. So it is, and I do this even when I've taught a class for a while. I usually go back and pull very similar questions to past exams. So that's a very good idea. Looking back at past exams, past exam reviews. The blank reviews are still up, so you can just kind of do them over again if you want. But yeah, that's a great idea. Yeah, I'm really hoping to do a final exam review. Well, I should. There's like 3 reading days, and if I don't have it done before then, I should get it done on the first reading day, so y'all have time for that. Because yeah, if you guys don't know, or just forgot, the 30th and the 1st, yeah, the 30th and the 1st, Monday and Tuesday after Thanksgiving, those are remote class days, but then the 2nd through the 4th are reading days. So finals don't start till the 7th, so you have like 3 days to be free and study, I guess. But anyway. So yeah, I'll stick around. If anyone wants me to talk about anything, let me know.
Could you go over the stuff we did last class? That was kind of confusing with the 4 exponent and stuff, the binomial.
Oh, the binomial theorem stuff? Yeah, sure. So how do I want to start this? Oh, sorry, Dakota. Dakota, no. What I'm gonna do for the final is it's going to be online because it has to be. But I'm not going to make you guys sit in Teams or anything like that. I'll be around Teams, so, or maybe just my email. I'll figure that out and I'll tell y'all later. But I'm not making you guys come to a specific thing and sit around, and because it's not worth it. So no, you don't need a video for your final. Ryan, is there a specific piece of it? Well, I can do whatever you want. But is it like expanding it? Is it just like you want to go over how this actually works? Is there a specific piece of it?
I just like to go through it. I don't have a specific part that I wanted to focus on.
Okay. So essentially what this is about is this is mainly for expanding these, polynomials to a power. So of course, just push that 4 through to both pieces. So essentially what this thing tells us is that we can essentially use these choose coefficients, if you will, to be able to find the very front coefficient for these pieces. So essentially, if I want to take some, let me see, some x plus 3 to the 5th, and I wanted to expand that out without having to FOIL it 5 million bajillion times, what that tells me is that essentially we have two pieces here. We have an x and we have a 3. And essentially they're always going to pair up, and the pairs are always going to have powers that are going to add to 5. So we're going to have a pair of, say, x to the 5th, 3 to the 0, and we're going to have x to the 4th, 3 to the 1st, and x to the 3rd, 3 squared. And I'm leaving space specifically, and x to the 4th, 3 to the 1st. And that's too much space. Yeah, I'm adding way too much space here. Anyway, and then 3 to the 5th. Let me, hold on 1 second. Let me clean that up a little bit more. Let me rewrite that. So we always pair them up so that their powers add to 5. So let me rewrite those really quick. 3 squared, 4th, 3 to the
Just so
1st.
you know, if I drop off, it's because my computer is not charging for some reason.
Oh no! And then x to the 0, 3 to the 5th. So essentially that's the one piece of it, is that it tells us that we can break this up, and all of those kind of terms are going to have their powers adding to 5, because 5 is the power that we want to expand this out to. So 5 plus 0 is 5, 4 plus 1 is 5, so on and so forth. And then the other piece that we need is we need to figure out these numbers in the front. And those essentially come from the binomial theorem, which tells us that the binomial coefficient is essentially going to be n choose k, where n is the power that we're expanding it out to, and k is the power of the second term. So essentially we're going to, whoa, I didn't mean to do that. We're essentially, since we're taking it out to the 5th power in this example, it's always going to be 5 choose something. So this is going to be 5 choose something in the front of all of these. And essentially we're going to take the exponent of the second term, or you can think about it as start with n choose 0 and go up until you hit n choose n. So we'll have 5 choose 0, 5 choose 1, choose 2, choose 3, choose 4. No. 5, 4, 3. What have I done? I screwed it up. Squared. Cubed. First. 4th. I really screwed that up. Wowzers. 5 to the 4th. So sorry, I got really mixed up, and after that I went to the wrong term. So each one of the powers on the first term should be going down. So 5, 4, 3, 2, 1, 0. And then the powers on the second term should be going up. So 0, 1, 2, 3, 4, 5. So we should essentially get every pairing of numbers that add up to 5. And at this point, we've expanded it out fully, and we would just need to actually figure out what all these numbers are and what they reduce to. So 5 choose 0, Lord, is something. So 5 choose.
I just wanted to say, remember how I was saying my computer might shut off on me?
Mm-hmm.
If it does, just keep going as if I'm still here, and then I'll watch the video.
Sounds good. So if we start figuring out what these actual numbers are, 5 choose 0. So that would be our 5 factorial over 5 minus 0 factorial times 0 factorial. So essentially 5 factorial over 5 factorial. So 1. So we get 1 times x to the 5th times 0, because anything to the 0th power is 1. If we do 5 choose 1, sorry, 5 choose 1, we get 5 x to the 4th times 3. So this would be from 5 factorial over essentially 4 factorial times 1 factorial, where that comes from 5 minus 1 all factorial. And then we have 5 choose 2, so 5 factorial over 3 factorial times 2 factorial. So 5 times 4 divided by 2. X to the third times 9, so 3 squared. 5 choose 3, so 5 factorial over 2 factorial times 3 factorial. So that's also 10. X squared times 3 cubed is 27. 5 choose 4 would be 5 factorial over 1 factorial 4 factorial, which gets us 5. X to the first, 3 to the fourth is 81. 5 choose 5 is 1. X to the 0th is also 1. And 3 to the 5th is 243. So essentially, once you have all of those numbers completely simplified out, oof. Anything to the 0th power is 1. I'm pretty sure I said that, but I wrote a 0. So we can reduce this to, so 1 times x to the 5th times 1 is x to the 5th. 5 times 3 is 15, x to the 4th. 10 times 9, 90 x cubed. 270 x squared. Whatever the heck 5 times 81 is. 405x plus 243. So if I was going to do one out fully, that's how it would go. Now, in terms of what you would be asked on your exam, you're never going to be asked to expand it out fully like that. There is one of them on the exam review that expands it out fully just because it's good practice. But in terms of what you could be asked is you would really only be asked about one of these terms. So I would ask something like, what is the coefficient of the x to the 6th term in the expansion of, let's go a little gross, but not terribly gross. 3x, let's do minus 2 to the 8th. Sure. So essentially we have to figure out what term that looks like when it comes to something like this.
Right.
So what that's going to look like, is we're going to have essentially, so we have one thing is that it always has to be a plus b. So we should think about this as 3x plus negative 2 to the 8th. So essentially, if we want this to be a 6th power, because that's what we're asked for, the 6th power, we would need to take that 3x and take it to the 6th power. So now we need to figure out what the power of the 2 is, the negative 2, sorry. So all of the powers always have to add up to the power that we're expanding it out to. So if we're expanding it out to 8, but we're only having 6 so far, the power of this would have to be 2. And then the coefficient in the front for the choose piece, again, is essentially power we're expanding it out to. And then we're choosing essentially the power of this second piece. So we're going to have 8 choose 2. So if we were to do this, we would have to figure out what 8 choose 2 is. So that would be 8 factorial over 8 minus 2 factorial times 2 factorial. Remember that when you have things that are multiplied together, you can just push through the exponent. You can't do that with addition or subtraction, which is why we have to do this scary way. But so 3 to the 6th is 729. And then negative 2 squared would be positive 4. Ooh, this one's a little bit of a big one, but let's see. So 8 factorial over this, we'd get 8 times 7 over 2 times 1 times, what's 729 times 4? It's 2916. So 8 times 7 divided by 2 is 28. And then 28 times the 2916. Whew, it's 81648. So the answer to that question would be this 81,648. Oh, and I think he disappeared. Rest in peace, Ryan. Yeah, he's gone. Okay. So that's the type of question that you'll see on your exam when it comes to these types of things. Anyone else who's paying attention is that you'll just have to find the generic term using the choose notation and then taking the two terms and making sure that those exponents on the two terms add up to whatever power you're expanding it out to. And then it's just algebra. Excuse me, I've got the hiccups again. So that's that one. Anybody else have any questions about any other topics, or question about this one, or anything else you want me to go over? Akarsh, do you want to go over that thing you were emailing me about, or do you want to go over that later? Exam, but if you want to go over it, we can. Oh, did he just disappear too? Oh man, he just disappeared. Okay. Well, we've got about 15 more minutes worth of class, so if you have questions, I'll stick around. But if not, y'all are free to leave. But if y'all want to look over the exam review and stick around and ask me a question if something pops up, they'll be here. I'm just gonna mute myself.